Hi guys, let's start. Okay. All right. Can you hear actually with this, or is it working? From the back you can. It's a bit. Yeah. Okay, good. So welcome to the fourth lecture on parallel programming. All right. So today what we're going to do is we're going to wrap up the slides here. We're going to finish discussing synchronized statement, locking in Java, and also discuss a little bit about the wait notify mechanisms, which you can use to coordinate threads. So last time we discussed a little bit about the syntax for synchronized and informally what it does, and today we'll see a little bit more examples and kind of some of the pitfalls that arise. Okay, before we start, somebody mentioned that some people are not familiar with the command line. So we provided this document that you guys can, yesterday Pavel wrote up a document that you guys can, so that you guys can use command line for some of the tiny examples that we look at, so you can play with them from Windows and Linux. Did you guys look at this, or some of you? So did somebody look at it at all? Yes, some did. Okay, so try it out and see if you have problems. Just email Pavel and he'll make another pass and refine it and so on. But it should be fairly straightforward. If you're in the computer science program, it's probably a good idea that you can use the command line occasionally. It's good to be able to do. Okay, good. So let's scroll to where we left off. So you guys are woken up already, so there is no need for this. The magic trick, you know. So you can play it with your friends. And let's go to the synchronized. This was the creation of the Java threads. We looked at that. How to start threads. And okay, we looked at that last time. And some of the key points that you need to start the thread. We started once. This was a couple of examples. And then we reached roughly, I believe it was here, around here, with synchronized. So we ended kind of like, so let's not use the projector because you guys cannot see the laser pointer. But use of the volatile, it's a bit tricky. So just be aware. And yeah, just be aware. Mostly just when you write concurrent algorithms, which you'll look in the second half. Okay, so the synchronized block essentially has the following syntax. This is where we left off last time. And what it does is it basically locks an object. Okay, so every object in Java has a lock associated with them. So every object has a lock associated with them. It's a little bit more general than a lock. It's called a monitor, but think of it as a lock. You can think of it as like there is a lock and you call, and synchronize calls the lock method on this lock. So it locks the lock associated to the object if it succeeds, okay? And right, if one thread locks the lock, then another thread has to wait until the lock is released, okay? And there really is no particular order in which the threads succeed in locking this lock. Okay, the VM does not provide such order. And so in principle, in some weird corner cases, you may end up with starvation here. If multiple threads is like trying to lock the lock and one always gets starved out because others succeed in taking the lock, okay? So this is where we were left off last time. It's a pretty simple construct, but there is like a bunch of pitfalls that we need to look at a little bit, okay? So there is a little bit of syntactic sugar here, where up top you see how you declare not just synchronized block in the middle of your code, but if you want to lock like the entire method that you're working with, you can declare like synchronized keyword like this with the method. So you can say like the method name up top is synchronized. So what this means is that every time a thread calls this method, it's going to try to take the lock. So that's what it means. The lock associated with the this object of the method name. So that's the first one. So that's essentially a syntactic sugar for just having synchronized block covering the entire method. Just a common thing, common syntactic sugar. And then the second one is locking a static method. So this, again, this static method, if you have a static method, you can actually lock that as well. And what would you lock exactly? It's a static method. Well, the Java Lang class itself is an object, so you'd essentially lock the Java Lang class, okay? The class associated with the particular object. So we'll see a couple of examples here because that's a little bit less intuitive than the first one, and it's also a bit less. It's less common than the first case, which is just synchronizing on the this object. Okay. So this is really the top one. These are really just shorthands here. So this is like how you'd normally use it. You'd have some file which is reading a file, file name with some name. And it's reading the file from the hard disk or from somewhere else, and then you would synchronize this method. Okay, so this should be fairly straightforward. I hope. Right? It's not. Oh, is there any questions here? Yes.
If you have two synchronized methods, you cannot run them at the same time.
So if you have two synchronized methods, like the top one, let's say in the top one we had like name1 and name2, like two, that's what you're asking. Like I have like name1 is synchronized and name2 is also synchronized, right? In the same class, right? Then if you have one thread that wants to run name1 and another thread wants to run name2, then the two threads would have to wait for each other because they would be trying to lock the same object. So the synchronized is associated with the object, this object, not with the with the method name per se. So if I have multiple methods in the class which are all have synchronized, then only one of them can run at a time. And if another thread wants to run the other method, they would have to wait. Okay. I'll see a couple of examples soon. Any more questions here? Yes. Yeah.
We have a method like with a parameter and an object.
Yeah.
And we access this object. Is this object and the parameter also there?
So if you have, let me repeat the question so others can hear. So what you're saying is, if I have a method and if it's on some object like here, and if I'm accessing, what I'm accessing?
I just run the method.
Yes.
With some parameter.
Yes. No, the parameter is not locked. Is the question or a similar question? So these are good questions. So synchronized is kind of like one of these, I don't want to say misleading keywords, but it's these like weird corner cases, how you can make mistakes. Let's see this like this here, just so that we are on the same page. Let's see our favorite projector here. And somebody gave me a piece of paper. Thanks a lot. There was usually lots of paper here, but somehow today there's not. So let's see here. If I have some method, let's call the method just like a void, I don't know, let's say it's some void method M1. Okay, I have some void method M1, and here, from his example here, just to follow his example, if I have some other object here, let's say that I have some object here, pick some type, I don't know, like let's say last time we had load, let's say A, I don't know, something simple. Okay, so I have some signature like this, okay, of some method here. All right. Let's say I have synchronized here. Synchronized in front of this object, right? So I have declared such a thing, public method or private, and now it's there. And this is part of some class, okay? That's part of some class. Let's see if you guys can see, like part of some class. Let's call the class test, just for fun. Okay, so part of some class here, and there's other methods here. So now what happens is, if the main program does something like, let's say, test t is equal to new. We are writing a little bit of pseudocode here, okay? So I do test t. I just create like a new object of this thing. And I call like t.m1 with some parameter. Well, that's taking a. Let's call it something else. Let's call it a1 as a parameter. Maybe here I created an object over here, like a1 is equal to new a, just to create this thing. like this. Can you see from the back? Or we can zoom it even. Like this. Magic zoom. Hop. Can you see? Yeah. Okay. So let's say we have this situation, and this TM1, okay, this is the main thread. So I'm just running the main thread, right? Just running the main thread. So what is this thread going to lock? What is this going to lock? What is this? When I'm invoking this guy here, the synchronize is going to have to be somehow taken into account. And so what's going to happen here? So it's going to lock. The effect of this is going to lock. Well, there's no other thread here. It's just the main thread, okay? So it's just going to lock the object. Which object? Which object is going to lock? Yes? The which one?
Oh, no, wait, the test object.
That object. So the object test, but if more precise here, we would say like the object referenced by T. Right? It's going to lock this one. And it will not lock object referenced by A1. Okay? So, this is what happens. Okay? I could have declared like this method M1 instead of having like the syntactic sugar here of synchronized. I could have just been, I could have just done something like void, or let's call it M2, just some other method just for. Okay, and I could have said, well, I don't want this synchronized outside. I just can do it here. And what would I put here? What would I put here? Let's see. You guys have to say. And this is the brackets, and then this is the, this is some code here that happens. Okay, and then this is the end of the method. So what would I put here? If I want to have, if I want to make sure that I have the same behavior as if I would have put synchronized in front of the method, what reference should I put here? Yes? This. So I just put this, and this is basically the same. Yes?
Would it make like any sense to put another object here?
If it makes sense to put a lot of object, where?
No, I mean, instead of this, put
Yes.
another object.
Yes, you could put another object. I mean, the syntax for synchronized allows this, allows you to do what you said, and you can do this. Yes, you can lock. Let's go over here. So let's say that you have some function. You have some function f here, or some function f. Okay, some function f, and I'm doing a bunch of stuff here. Doing a bunch of stuff. I don't know what, I'm doing something. And then maybe here, maybe this is taking as parameter something, but let's say that I can synchronize on what, for instance, here? Let's say I can synchronize on, let's say that this class test, just for the hell of it, we had, let's say that there is somebody in the class called Philip. It's a wild guess, but it has to be somebody like this, right? Philip, but we'll write it like in short way. So let's say there was like a static object f. No, let's not call it f. Let's call it let's call it f1. Doesn't matter. Some object here of type. So I have an instance here of type Philip. Okay, some static object of type Philip. Okay, it's here. And then what you can do here inside the method here, you can do something like over here. You can refer to all kinds of things. You can say like test, for instance. You can access a static variable. You can say like test.philip, because Philip is a reference of some kind, right? So I can, here in the synchronized, I can write expressions that refer to objects. And these objects can be, these expressions could be coming from the parameters of the method, could be this, could be something else. Right? Question, yes.
So two synchronized methods can be managed by different ways, but if I do two normal methods and then with synchronized blocks and then the different objects as blocks, then I can run both.
Yes. Yes, you can.
It's not the same one.
Yes, let's see here. Well, we'll just continue our example to answer the question. Let's suppose that Here I have F, right? I'm locking on some object. I'm locking on some object here, test Philip. This is just some static field that I took the object from there, right? I'm just locking it. And then maybe here I have another method. Let's call it another method, or let's make it so another method Q, I don't know. And this Q is doing synchronize now on some other method here. Let's say, let's say that this was taking some parameter. Maybe let's say this had some parameter B, object of type B. So I can do like log B and then exit this thing. Right, so these two guys, this one is locking some object B, and this one is locking some object that exists, that is referenced by static field. So these two methods here, F and Q, if they're touching different objects, if this object here is different than this object here, then they will run in parallel. There is no problem. Does this make sense? So unless the locks overlap, unless the objects overlap, there is no issue. Yes?
Let's say there is a reference P1 which references to the same object as P2. Is it then locked for P1?
Wait. So there is a reference where?
Let's say you have the reference P new.
This one here? Back to this? Yeah? T1 is equal to T, yes? Yes. Yes. So now the question is, in this case here, what happens if, it is doing something like, let's say, if the references are pointing to the same object, then you're going to lock that object because you're always locking the object, right? So if it turns out somehow that this guy here was the same object as this one here, let's say, for instance, this is of type B, and B was a subclass of F1, and somehow it happens that, this B here and test Philip is basically the same object, for instance, right? Then, when you are locking them, you're going to lock the object. So even if you have like 10 different variables, and I'm locking on them, if they're referring to the same object, then you're going to lock the object, basically, all right? So this is what happens. So you're locking the object, right? This is why I said very carefully here, we lock the object referenced by the variable, okay? Okay? Does this make sense? You lock the object referenced by the variable. This should be very clear. If there is any questions, now is the time. Or it's super clear. Is synchronized super clear? Yes?
What exactly does this log do? Does it? Can you just? Are you able to change the fields, or are you also able to call methods?
Mm-hmm. Okay, good question. What does the lock actually do? Yeah. So what happens is, once you take the lock, once the lock is taken, let's say here, okay, here the lock is taken because this is synchronized over here. If another thread comes and co-synchronize on the same object, it will block. That's the only thing it does. I lock this object, I lock it. If somebody else wants to lock it, they're going to block and wait for me to unlock it. They cannot do nothing. Okay? So yes, more questions. What does it mean to block it? It's gonna wait. It cannot continue. So it just comes, it co-synchronized, and then just stops because some other thread has co-synchronized on the same object. It's just gonna stop. Yes. First, yes, you go.
If void f is called, or let's say q is called, some thread calls q, so
Yep.
the object b is locked.
Yes.
Then another thread can't even read from b, so it can't read its q.
No, so let's be very clear. When you are calling synchronized, if you succeed, you have locked the object. Okay?
It's invisible, basically. You can't do anything with it.
No, I have locked the object. I succeed in locking. Now, if another thread comes and starts accessing some fields or doing things to be or to code inside, like let's say that I have something like this. I do synchronize. We'll look at it in the later slides, but essentially what happens is the synchronized only protects you against other threads wanting to lock the same thing. If another thread wants to access some fields without taking any locks, it can do that. Okay? It does not block them unless they try to touch the lock, unless they try to lock. If they're adversarial and they say, I'm not going to lock nothing, I'm just going to touch everything in memory, it's going to do nothing. I'm going to have my lock, and you can still access everything you want. But if you also want to take my lock, you're going to block. So we're trying to cooperate in some sense. With the locks, we are trying to make one thread wait for another, wait for the critical resource. But if somebody is non-cooperative at all, then they're just going to... Yep. Sorry, what? No. So you cannot do it. That's why I said it has to be a reference type, right? Reference. So if you do something like, let's go here. If you do something like synchronized, I don't know, x, and x is of type integer, then there will be exception here. The compiler will complain, or the verifier will throw an exception. Yeah. Your point, you are, yes. Can you access public variables from a locked top? You mean, can you access the variables of an object that is locked? Yes.
We synchronize this and we try to read or write to some instantiated variable that then we modify it and synchronize it from another thread.
So if you have something like this, let's go up here. Okay. So let's say I do synchronized on this, right? And there is some code here. This code here can, of course, access whatever it is accessing. If another thread, so let's say that this accesses here is doing something like this. Let's doing something like this. What are you guys discussing there? Hey, my friend. No, behind you. If you have questions here. So I have this.x, and I do 5, right? And if I do this.y equal to 7, I have such a code here. Okay, that's my code. That's my code here, inside the synchronized. And now the question is, and this is done by one thread. Let's say this is thread 1. Thread 1 is doing this code here. Right? This is what thread 1 is doing. And now there is like another thread 2 here. And now your question is, can thread 2 do something like, let's say it's the same this, they have access to the same reference, and the other thread can do something like this x equal to 6, for instance. Yes, it can, unless this thread also takes the synchronized lock, in which case it will block.
So synchronized only locks all of the methods, not the entire block.
The synchronized only locks the object, nothing else. That's it. Synchronized locks object. So if I'm a thread and I synchronize on this object, I lock it, and I can do all kinds of accesses there. If some other thread comes and wants to access fields of this object and it has not taken synchronize, it can do that. Nobody blocks it. So this is why synchronize is a bit of a pitfall, because when you write something like this exactly here, people imagine that whatever is being accessed here is atomic. Nobody else. This executes atomically. It's like lock and boom, it executes. But that's not quite true. Another thread may come, which has not taken a lock, call it an adversarial thread, that you made a mistake maybe, and then it can touch these things here. We'll see a little later. This is an example of something called weak atomicity. Strong atomicity would be that this literally here is like, boom, one step. But that's not the case in Java. Yes?
If one thread logs an object,
yes.
for whatever reason dies, will the log be released or will it be continued?
Oh, these are hard questions, my friend. If a thread dies. So we'll see examples of where the thread... so there is a log cleanup associated with it, yes. The VM is going to try to do this. There is blocking operations that can happen. It's essentially blocking operation inside synchronize, in which case it's going to release the logs. Tries to release the logs. Or an exception happening inside the synchronized block. What happens then? You've taken a bunch of logs, now exception happens. Also have to release the logs. So we'll see examples of all this, okay? So the most important thing is, so synchronized on some reference R, this logs object referred to by R. And that's all it does. If somebody else calls synchronize on the same object, it's going to block. That's the only thing it does. And with this functionality, you need to implement whatever atomicity and mutual exclusion it is that you want to implement. Okay? Yes?
If I have a method which is synchronized on R and R is blocked, but within the method I'm not doing anything with R, I just do something else, does it execute or not? Probably not, right?
So, okay, another question. Actually, let's maybe postpone this because we have exactly examples like this coming up. Okay, but just remember this. So that's important here. We'll see it again in an example. Synchronize does not have the semantics of what you think it does when it, as far as atomicity goes. It does not execute the whole thing in one go. It's only atomic with respect to other threads who have taken this lock. That's it. That's the best way to imagine. It's atomic with respect to whoever cooperated in taking the lock. Okay. Another question.
And just so I understood you right.
Yes.
That it's only atomic in regard to other synchronized nodes. Do you mean that?
Other threads taking this lock.
Oh yeah.
Yes.
That's what I meant.
Yeah.
Do you mean that despite me logging an object, it doesn't mean that I have to do everything within the block at once, but I can take the log, do have the operations in the synchronized block, do some other operations.
Could be. Yes, you could do it. We'll see examples. So that's the granularity of locking and all these kind of things. For now, what's important to understand is that the synchronized, synchronized method is a syntactic sugar for just a synchronized block on this. Okay, if it's an instance method, and the fact that synchronized R just locks the object which is referred to by R. And you cannot do it on primitive types, just on reference types. Arrays are also reference types. You can lock arrays, the array object. Okay. So let's move on. But unfortunately, synchronized, it's kind of like one of these constructs that looks, it looks intuitive, but there's a lot of weird corner cases with this happening. Okay. So actually, somebody had an armor. Nothing. Okay, good. So let's go back here because, yeah. All right. So this was supposed to be the summary, but okay. I hope you guys got something out of it. But it should be, given what we went over now, this should be fairly direct. So one thing here that you should know is that synchronized locks are reentrant. So what that means is that over here, if you have a synchronized method F, and in the same class, you have a synchronized method G. So these are instance methods. Then when I call F, when I call G, I'm going to take the lock on this. Okay? If I succeed, I take the lock on this. And once I'm inside, when I call F, I am going to succeed. Because I've taken the lock, I already own the lock. If I call again the lock, if I again want to lock it, it's just going to be a counter, if you like, is going to be incremented, that I've locked it twice, if you want. When F finishes executing, you unlock it once, but I still own the lock, because I locked it first when I call G, and when G finishes, I'll finally unlock it. So they are nested, meaning that think of it as a counter that gets incremented. If I own the lock, if I call the synchronize again, the counter will keep getting increased. Okay, makes sense? Okay, so that's that. Why is this existing? That's a design decision in the language. For some trading system, operating system, that's not the case. You will deadlock yourself. If you code the lock again, it will just block. And then one of the reasons why this was there in Java is to prevent, let's say, some programmers from deadlocking themselves. Also, it allows you to kind of write more compositional code. Like if you have lots of libraries that are nested, you just focus and say, this is atomic. And I worry only about this. I don't worry about kind of global reasoning, who can call which lock. I just say, this is atomic. If you code another method of my library, and I want to call a nested method like here, then things will be things will work well, just like you would expect. But this is just a point here that just don't forget this. Okay, all right. Most people don't notice it. They just it's re-entrant. Okay, that's another point that was just asked as far as synchronized goes. These are just like different points you should be aware of. So here we have a shared variable called C, a counter, and we want to increment and decrement the shared variable and also read its value. So we have 3 methods in this class. One increments, one decrements, one reads the value. So here I have synchronized them all, and this is what you would expect to happen. I synchronize them because otherwise, if I have multiple threads who have access to the shared counter, I want to make sure that the value of C is consistent, and things happen as you would expect, like C++ there or C++ does not get preempted in the middle, and we'll see examples of this. Now, it's important to remember, especially if you're coming from the sequential world, and this we looked at last time, just don't get confused with this. That's a little bit tricky. Oh, not this one. There's like, no, this is the one. What's happening? Oh, it's here. Okay. So one thing it's important to remember is that if you're coming from the sequential world, is that if you have a statement like this, like we had on the slide there, something like C++, okay, C++, this thing, it's on purpose there, okay. So this at the Java level looks like one syntactic thing like happening, and especially when I C++, like plus, it looks like, okay, counter gets incremented, but underneath what happens, okay, you'll see some bytecodes or instructions, is that first C is going to be read, then R1 is going to be incremented. This is a local variable R1, some local variable, and then finally C will get assigned this local variable. So here I have a shared read from C, shared read, and here I have a shared write. So underneath, so this is in Java here, and this would be, let's say, in machine code or JVM bytecode, it doesn't matter. Let's say it's bytecode, doesn't matter. But the point of the matter is, this is not an atomic statement, even though it appears so in the language, this C++. Right? And this is an atomic statement. Now you just read the value. This is an atomic one, and each one is this is not atomic, but it's a local variable, so it doesn't matter. Nobody has access to it. So this is non-atomic, but it does not matter. But this is an atomic, if you like, atomic shared read. You just read it and you just write it over here. So each of them is kind of safe individually, but together they're not safe. Because somebody can come in the middle, as we'll see examples, some other threat and kind of preempt you and do damage, okay? So I think we even saw examples of this last time. And so it's important to realize this thing. And when you are, to be safe, okay. So you want to be safe with C++, right? I have synchronized. I just put synchronized here, whatever, well, let's put like this, let's say. So I lock this thing here to make sure that this is safe, okay? So if you're touching shared memory, typically it's good to think about this synchronized, and it's not, and we'll see a couple examples in a second. So this is why there is synchronized around it. Okay, does this make sense? Okay, you're touching shared memory, you're accessing and make sure that it's done under a synchronized, yes?
It goes before that if you have synchronized something, no other thread which another log cannot access.
Yes, another thread cannot access it, yeah.
This would be, it would be a design decision to not synchronize this, like allowing this thread to manipulate because it's only doing an action which would not
exactly
influence the
exactly, yes, exactly. That's exactly the reasoning. So what he's saying is, if I have a program, this is what I said last time, it's very important to understand this. By default, things are not synchronized. And by default, if you have parallel program and you're not synchronizing, likely you're going to have a mistake somewhere. And in order to satisfy the property that you want, you have to synchronize explicitly yourself. So that's what happens. Now, how do you synchronize? Now, notice something interesting here. In the first example, is that I'm synchronizing on an object up there, this object, but I'm protecting a primitive access variable C. Ideally, I would have just wanted to synchronize on C and just say, well, C is atomic, leave me alone with these objects here. And there is classes that allow you to do this for some atomic counters and some other things, some basic libraries that Java provides. But in general, even if you have some complicated primitive manipulations of primitive types, you may have to lock an object. It's kind of like an auxiliary object, if you like, there. This is just to lock the C, really. Okay, so that's one point, just notice this. And the second point when you're doing locking is to make sure that you are aware of what he asked earlier about synchronization granularity. So if you have a method, so this is typically where a lot of the mistakes happen also. So if I have a name, so add name, some method here, and I'm doing some manipulations over here, say, let's say this name count is some shared variable between multiple threads who can access name count, and I want this to be safe, so only one at a time can access it. So I'll just lock it here. Now it synchronized this. And I'll do this. And then I'll say, well, this thing here, adding the name to some map or to the list, is expensive. I don't want it to be under asynchronized because it's expensive, and I don't want to block the other threads while I'm doing expensive operations inside synchronized. That's like a logical thing to say, right? Oh, I don't want to block other threads. I'm doing something in synchronized. Let me quickly finish my job in the synchronized and do all other operations that are safe outside. So this kind of thing people often do. They're like, well, let me identify the critical operations, lock them in, so other threads cannot manipulate, and let's do try to push the expensive ones outside the synchronized, so it's kind of local, only I have access to this, and so on. And so this may be correct, may not be correct, depending on your application. So these lists are usually concurrent collections, so this may be fine, but it could be the case that you want all of these statements to happen inside synchronized. It depends on the property that you care about. The high-level point here is that there is this notion of synchronization granularity, how much it is that you are locking. Does this make sense? That's important also. A lot of the mistakes happen here, especially people try to get cute, and they start here and they lock everything, and say, oh, no, I can put this outside. Okay, they put it outside, boom, something gets violated. And so you have to be very careful there. Just be careful. Okay, so this synchronization and granularity is another point, okay? Any questions here? Yeah. Yes, him.
What is atomicity again?
Atomicity, we're going to see it in a second. It was here before, right? It's on this slide here. It just means that, so first of all, there are many answers to this, but it's actually a hard question, surprisingly. Atomicity can mean that one notion of atomicity is when I say these statements are atomic, it means that they execute and nobody else, no other thread can preempt me in the middle. So nobody else can touch nothing. I execute it as if I'm doing like one atomic unit, like a one instance in time. Okay. So this is a notion of strong atomicity. We'll see the example in a second between strong and weak atomicity. Atomic just means one instruction, like boom. Nobody can preempt me, okay? And there are different notions of atomicity, actually. There are many different notions, yeah, okay. So we'll see this strong versus weak atomicity. Okay, so a couple other points about synchronized. Well, here is like, if I have, that's another optimizations people do sometimes. If I have two variables, C1 and C2, now I have two counters, okay? I may want to make two objects on which to synchronize because they're disjoint counters. So I may not use one object, but two objects. So I can get more parallelism, like more threads can run. So here I have the increment, and if I increment C1, I'm using lock 1, and if I increment C2, I'm using lock 2. These are disjoint variables, and I want them to be, threads who are only want to touch C1, they're just locking this one. I don't want to have a common lock for both of them because they're just disjoint variables. So I may do such an optimization. Right? Just have. I could have done this by just saying, have one synchronized lock, just one. You say lock one everywhere. This would reduce my concurrency, my parallelism, because everybody has to wait now, even regardless of which variable they're incrementing. So this is also trying to kind of increase parallelism and threads being able to run without blocking too much. Okay. So these are just small patterns that arise. So I think that's roughly actually as far as synchronized goes, as far as the patterns go. And then we'll look a little bit at, I have a few examples for you about how deadlock can happen, what's the difference between atomicity and synchronized, and also about non-determinism and synchronized. So there are a few properties, how they relate, that we need to look at by example. And then we'll be done with synchronized. So let's take a quick break, and then be back with, actually wait, no break. What is going on? There are two clocks here. No, my friends, you have to say no break. 4 minutes still. Dear God. Okay, there are two counters somehow on this. Okay, we have still 4 minutes, officially 4 minutes. Okay, so this is the synchronization with different locks. Any questions here? Okay, different lock synchronization, okay? Here is another one that start getting a bit more messy here. So here I'm doing a synchronized on a static method, like we had initially with the syntax. Like I'm just doing synchronized on a static method, get screen. So what would the effect of that be? What is this actually locking? Okay, what is this actually locking? So think about this. Yes. Huh? Locks the static class. So what you're saying is if I have multiple threads who are calling this static method here, they're going to block, right? Yeah, so it locks the static class, which is also an object itself. Okay. Once you, now you see the synchronized, you can lock the object, or you can lock a class, which is also an object, so you just lock these things. And you put code inside the synchronized that you want essentially only to be kind of executed in a mutually exclusive fashion. So anything inside the synchronized, ideally, nobody else can touch. And if they want to run this code, you have to also make them take locks. Okay, so here is an example. And what is happening here? This was the example actually just that we drew there with C++. So again, we use the pseudocode notation here. Just I have thread 1, I have thread 2, and this code looks kind of safe, okay? So it's basically, I'm locking this object, and then I'm executing some operations. Essentially, I'm doing C++. And I have T2, thread 2, and I'm also doing incrementing C, loaded to a temporary variable, and then increment the counter, okay? How many interleavings do I have here? How many possible executions do I have? How many ways are there for the threads to interleave? It's 2. Either T1 runs first, takes the lock, runs first, and then T2 runs second, or T2 runs first and T1 runs second, okay? So I only have, when you see this term interleaving, it just talks about how the threads are with relation to each other in the execution. So here I have labels 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Okay, this one ran first, took the lock, and then unlocked it when it's finished. Or this one ran first, 4, 5, 6, 1, 2, 3. So I have 2 interleavings here, okay? Just to be clear on the term interleaving here. Okay. Here is a common mistake with synchronized. Same code, except one of the lock is missing. And that's back to the question of atomicity here. It's this question, many people ask this question. That's probably this is probably the most common mistake. So somebody came here and said, I'm doing C++. Oh, we have a break, okay. So let's come back to this after. Okay, so back to the, back to the examples. Okay, so we have this example here. And there's lots of good questions. I mean, many of you guys, I think, got it. So I think that was a good summary by somebody who said, like, I mean, ultimately, it's if you put too much synchronized, you gain correctness, right? You get, let's say, more correct in some informal way. But if you put too much synchronized, you may get more inefficient because more and more threads will block and wait for each other. So there is this trade-off between correctness and efficiency, always in parallel programming. Very explicit here because of the synchronization. Okay. So let's see this example here. What's happening in the example? We have thread 1 and thread 2, this pseudocode here, right? And over there on the left, on your left, this guy has taken like synchronized, and this one here has not taken synchronized. And because that's the case, this one is completely unaware that of any synchronization going on. You made a mistake probably here, forgot to synchronize. So the execution that you can have is this T2 can take a step, that's 4, and then thread 1 can run fully. It runs fully, and then 5, 6 continues after. That's like one possible undesirable interleaving or undesirable execution. You can think of other executions. Can somebody think of another bad execution? I mean, you guys hit the break, but like maybe somebody else. No, not you, no. You know, I think you know this. Somebody else has to give something. Yes. Yeah, I think you know. So this, yes. 1, 2, 4, 5, 6, 3. 1, 2, 4, 1, 2. This guy does some steps, and then 4, 5, 6, 3. Is that possible? Yes or no? If you bet the house, how many say yes? All right. So it's possible. You can do 1, 2. This thing there is completely unaware of any synchronization. It just runs, and then this guy continues. Yep. Yep. Can a thread be interrupted while it's in a synchronized block? While it is running a synchronized block, you mean? Right? Yes? But what would that mean? Like, what it means when you say interrupted, you have to call the interrupt method, right? If you call the interrupt method, we'll see that later, a sticky bit will get set, but you will continue execution unless you are blocked on something like sleep. Then you catch interrupted exception, and then you have to catch it and do something. So we'll see how interruptions can interact with the synchronized and waiting a little later. But yes, it will not stop you and throw exception immediately. Like you get set the bit, and you may have to check if you are interrupted and then do something. Or if you are waiting on a sleep or wait, then you get interrupted and you have to catch the exception. Would be inside synchronized. Does this answer the question? Or? Okay. So, basically common mistake that can happen. Why is the mistake happening? Because people think that when they do synchronize, the whole thing is atomic. They're like, I put synchronize, so the whole thing is atomic. It's not. It's only atomic with respect to other threads who took a lock on, who want to take a lock on this object, in this case, this, a reference to this. Okay, now just a common pitfalls. What's this here now? It's another mistake, yes. That's a second one. Well, that's an easy one to spot. I mean, this is just, actually, is it a mistake? So what happens here is that we again have the same code, kept the same code, but now the expressions there are this and p. So this one is locking the object, which is referenced to by the this expression, and this one is locking the object, which is referenced to by the p expression. So p and this are references. So is this a mistake? That's the question. What do you think?
Well, it's your conscious decision to lock something or not. So
yeah.
Maybe it's intended to work. So it's like...
But let's say that I want at the end to have the semantics that, well, I'm at the end, I'm starting with C0 and I want to have 2 at the end, right? This is what I would want to get, right? So is this a mistake then? Yes. It's a mistake. It locks something else. Another opinion, okay? As you're doing this, I don't know what it means. Okay, it depends on what P references. Yeah, almost correct. It's correct, but yes. So what it means here, you have to be careful, right? So you can syntactically write something like this and P, or like X and P, or Z and P, or something. People are like, oh, it behaves. These are different because variables are different. He asked it over there earlier in the first half. But if these two guys are referring to different objects, there may be a reason to assume this because of our application, or would need to know that they are referring to the same object for this to be correct. That this and P are referring to the same object for this to be correct. Because if they're referring to different objects, you will get undesirable behaviors, right? Does this make sense? So what that means immediately, like you see this, like I told you, like in the second lecture, like concurrency interacts with aliasing with heap, and heap in the sense of objects, with objects, and how references interact with these objects. So in concurrency, there is this intimate interaction between kind of references in your Java heap, in your Java memory, and your program, and the synchronized and other parts. So yes, if this and P are different objects pointing to different objects, it's wrong. And if they're pointing to the same thing, then it's same object, then it's correct. Then it would be what you want to get. So what do you want to get from this code? You want to get 2. So what you really want to do is you want to treat this as atomic, right? Fully atomic. That's what you would want to have. You want to have this kind of strong atomicity kind of thing. So let's look a little bit of more examples here. Okay. Somebody took it or not? It must be here. Okay. So let's look at a few points about synchronized pitfalls that you guys should avoid, if possible. This is the zooming. You guys can see on the back if you can see. You can see if you can. Okay. So let's look at some examples here. A little bit in pseudocode, but in Java you can write it pretty directly. So let's do like this. This is such a long thing, I'm almost tempted to put like sync, but I'll write it like this, not to be lazy. Synchronized A. Okay. Okay. And okay. So one thread does this, thread 1. And another thread does this. What do I want to write? Can you predict? Can somebody complete the bug for me? What should I write for the bug? A. Okay. So I wrote it what you say. You screwed us with this code now. It's your fault because of the A, but that's what it is. So what has happened here? Synchronized A, synchronized B, and the other one is doing synchronized B and synchronized synchronized A. What can happen here? Yes. Deadlock, he says. Okay. Deadlock can happen. Let's just number these things just to make sure. I'm just numbering them so we can refer to them. Okay, 1, 2, 3, 4. So what is the sequence that leads to deadlock? No, you already said it. And no, you cannot say, he cannot say. You can say, you. 1, 3, and then? 2, 4. You get deadlock. I mean, the thing blocks, right? Definitely blocks here. What the heck is deadlock even? What does that mean more formally? Okay, we have to see what that means a little later more formally, but intuitively it just means that no thread can make progress here. They're blocked, like waiting for each other, if you like. If you come, After this, I can show you a bit more formally. I don't think you need it for now. It essentially gets a cycle in the execution. But let's not get into this now. I think you need, this is important. I'm showing you this because it's important when you start coding, so that when you're coding, you're aware of these issues. They're not explicitly mentioned in various places. So this is one. Okay. So not all executions lead to deadlock. Maybe I do 1, 2, and then I do 3, 4, and it's fine. Okay. Okay, so this is one here. Deadlock, a block, essentially, wait on each other, okay? So this is one you should be aware about. Now, there is another point you should be aware about, especially when you're coding, and this is this point here. There is this thinking, which is, and let's see, just so that this is too pessimistic versus optimistic. What does that mean even? Okay. Synchronization. It's just these 2 points, pessimistic versus optimistic. You see them used a lot. It's like optimistic versus pessimistic. What does that mean? So let's look at this example here, just to show the point. I have a thread 1, and I have some, let's say the thread is it's executing some function T1, and it is doing, in the function, it is doing something like A of I is plus equal to 10. A of I plus equal to 10. It's updating some array. A is some array. Okay, A is some array, and in parallel I have another one, some other index J, and we are writing a bit of pseudocode here, which is updating the same array plus equal to 20. Okay, so we have an array. We have some array here. Okay, some array, some big array. No. Tuck, 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 tuck. Okay. Now, what's happening here? This is a very simple problem. I want to be updating the entries of this integer array. Some integer array. With multiple threads, they're doing some work. They're updating the entries of the array. So what's the situation? Well, what happens is that, this thread first one and the second one, and maybe they're invoked inside the loop, outside there constantly. Like we can put a loop around here, around these guys here, some larger piece of code. Okay, but ultimately the point is that, let's say in most of the cases, in 99% of the cases, T1 is working here. So 99% of times, T1 is operating on this part, and then T2 is on this part. So T2 is 19. It's most of its time is spent here. 99% of its executions are just here. So it mostly you run it and just they access the joint part of the space. That's what they're doing. Okay. So this I can differ. So sometimes this guy is like 0, sometimes it's 1, sometimes it's like 2, 3, 4. Sometimes it's like T of 1 is 3, updates entry 3, sometimes it's 1, but it mostly stays this half, and mostly this guy stays here. Okay? So if they're fully disjoint, and I can show that this index here and this one, they just never touch the same part, I don't need any synchronization. They can just work, right? They're just touching different parts of the memory, so why should I synchronize anything? That's a common case in GPUs, for instance. Somebody asked last time, a graphical processing unit where deep learning runs another workloads that are known, and they typically have like mostly disjoint accesses like this, lots of threads, processing some matrix or some array, 2-dimensional array usually, doing some computations, that's fine. But what happens now if occasionally in the weird case, we are at number 13, okay? And occasionally I is 13, I is equal to j is equal to 13. So they just want to occasionally, 1 in a million times, want to touch this thing. What should I do now? So, what am I going to do now? So there is synchronized thinking, which kind of says, well, these i's and j's are in different threads. What am I? I'm going to somehow stop the threads and check the i's and j's that are the same. That looks weird. So the synchronized thinking is, you can make it more optimized, and you can, yes, but synchronized thinking says, synchronized thinking says, why don't you put a synchronized here? Put on some lock, I don't know, think of some lock here and put a synchronize here. So synchronize some lock here. So everything is under a synchronized block here. Same lock, everything is locked under the same synchronized. We are safe. But that's back to his question, whoever asked this question. Well, but now I'm blocking the entire application 99% of the time, like this thing is blocked here for no particular reason. We have to wait for each other. And if this is an expensive computation here, not just adding numbers, you're just like blocking the whole thing. Okay, so this is in kind of to illustrate pessimistic synchronization. Pessimistic synchronization says, pessimistic synchronization, I'm paranoid, you're paranoid, everything can alias. God, let's put synchronized everywhere and then just like be paranoid about it and anything can happen and do this, okay? Optimistic synchronization says, hey, most of the time nothing aliases, threads are touching disjoint memory, right? They're not really interfering. Let's just not synchronize them most of the time. And so in the synchronized is kind of a, if you like, more pessimistic synchronization. With it, you can implement optimistic synchronization, but by default, somehow when you're putting these things in the code, it's more like a little bit more pessimistic. We will not study this in the course. Maybe Torsten mentioned it in the last lectures. Instead of doing locking here, or you can implement locking with certain hardware primitives internally, such that these two statements are really executed optimistically. So always in parallel, unless there is a conflict, in which case the thing will backtrack from the beginning and then take the locks. So there's some advanced mechanisms called hardware transactional memory that is optimistic. You don't have to worry about this here. Here, as far as locking goes, it's kind of pessimistic. I take the lock and I'm blocking and that's it. The other thing that you need to notice here in this example is the fact that synchronization is, let's say, control-driven. Synchronized statements, are really, you're splicing them in the code. You're saying this piece of code should be atomic. That's what you're saying. You did not say, I want the data to be processed atomically somehow. It's not a data-centric view in some sense. It's more of a code-centric view. So synchronized really is more of a code-centric view. Okay. A data-centric view would be to say, I want this to be accessed atomically. I don't care how. You figure out where to put synchronize or what primitives you're going to use, and you'd program your application by just saying, I want this to be atomic. I want everything here. Every cell to be executed, every cell to be, all the operations on each cell to be atomic. How you're going to do synchronized or some other primitives, that's your problem. On my program level, I do this. There are such programming models that are less popular. Okay, we'll not get into them. That people can just say what part of the data is atomic. But just for your understanding, just to be aware, synchronized is really more of a kind of a little bit more pessimistic view that most things are non-disjoint and you have to, if you want to make them disjoint, you have to make them disjoint in memory and somehow coordinate to make sure that they're disjoint and then lock the relevant pieces. And it is a code-centric view, like you're changing the code to put the synchronized there. So that's just kind of a side effect, if you like, there. Okay, so now this thing came up several times in the questions and in the discussion, and we are kind of hiding it in some sense. We never really talked about the property that we want to enforce here. And somebody even said it here. They say, I think you said it, right? He said, well, sometimes you may not need certain kind of synchronized if you care, or if your property does not require it, like the specification that you want to enforce does not require it. And conversely, the presence of synchronized does not always enforce the property that you want. So let's look at these properties here that are important. Something like non-determinism versus synchronized. This is kind of intuitive. It's not really a surprise, probably. But if you have something like that again with our counters, and I have T1 and T2 here, okay, and I do something like this. I do something like synchronized. Let's say that I'm locking A, okay? I'm just taking the same lock here. It's kind of intuitive, but let's just write it for completeness. And here I'm doing something like C is equal to 1, and here I'm doing something C is equal to 2. well, this is kind of like, assignment to a variable. Now here at the end of this execution, what are the possible values for C? Huh? 1 or 2, depending on the order in which they execute, right? But if I am a writer of an application, I may want my results to be deterministic. I may want to say here, I only want C to be 1, let's say. I want it to be deterministic. I want for the same input, when I run these things in parallel, whatever threads I'm creating, I want at the end to get the same results as if I ran them, sequentially, like one after the other, let's say. Always to be the same. So I want the result to be deterministic, and this is particularly a particularly important property, like if they start from the same state, no matter in which execution they happen and interleave, I want the result to be the same. That's determinism. Does this make sense? Determinism? And this in data parallel workloads like GPUs and others, that's a common property. They have lots of threads, lots of activities, and at the end they say, well, look, I want it to be deterministic. Do your optimizations, but give me the same result every time. And now the point is, so what? The fact that you use synchronized here does not mean that you enforce determinism. And that's a very simple example where it doesn't happen. I mean, that's a trivial example. But some people, they say, well, I want deterministic. Let me just input synchronized. Oh, no, actually, this doesn't work. So this is just this point of synchronization does not enforce determinism. It doesn't. Okay. So that's another point. Just keep it in mind. Okay. So this is just common things that people kind of make mistake. Okay. Now let's see this question that kept appearing on atomicity. Okay. So ideally, you want to do something like this. Atomic X plus plus. And this thing is executed just one instance, one instruction. Nothing can interrupt it in the middle, none of these interleavings can happen, none of this stuff. Okay. The problem is that so this is something that's called strong atomicity. Okay, so it's just like what you intuitively expect, like I just put atomic and everything is just atomic and that's it. Now, with synchronized, just so that, again, we are hammering this point just to make sure that whatever, let's just put some lock here. When I do something like X plus plus, this is really weak atomicity in some sense, right? It's just, it's weak in the sense that this thing here, as we already saw, is only atomic with respect to others who are taking this lock. We already saw this before, right? So this is just what a programmer may expect. So don't expect this when you use synchronized. This is strong atomicity. Just what you would expect, fully atomic, fully everything happens immediately. Versus synchronized, which is a little bit kind of a weaker atomicity, if you like. It's only atomic with respect to others who took the lock. And if they did not take the lock, well, all bets are off, basically. So just differentiate between this. There's other variants of atomicity and what's allowed and so on, but we're not going to get into it. It's just this atomicity versus synchronized. Just make sure that there is no such statement in Java. There is other data types that you can use that provide some functionalities for increments, decrements, and so on and so forth that we'll look at later. But this is the main statement here, and that gives you this weak kind of atomicity. And we saw examples of this with this C++. Okay, any questions here? So this we covered here, okay. Good, last point, and I hope you covered this in the intro to programming. This happens a lot in HPC, high performance computing applications, but the point is more fundamental. It's about the floating point associativity. Who knows about this problem? Did you cover this? This is the basic of floating point. This is not a question of parallelism. So in floating point, you should know this if you're working with floating point and concurrency. It's a bit surprising. If you're writing this kind of code, in floating point arithmetic, because of the approximation error used by the hardware on a real machine, A plus B plus C, this does not hold. So its floating point is not associative. So the addition is not associative. What does that mean? What the heck does this have to do with concurrency? The problem is, and this is a problem in some applications, so you should be careful when you're using floating point types. Okay, when you do synchronized on A, again, we are like being safe and all this, like just like we learned in the lecture. Okay, and let me write it like this. We have two threads here. Got the synchronized, it's just like, oh, mamma mia. Okay. Okay, and maybe C initially is 0. So we have this piece of code here. We have two threads, thread 1 and thread 2. Okay, they're executing the synchronized blocks. I took the lock like A, just like they say in the lectures, like this guy tells us in the lecture. I took the lock, took the same one, all fine, locked the object. And now I'm doing C is equal to C plus 1 and C equal to C plus 2. You expect at the end to get C is equal to what? No matter which execution runs, what do you expect to see at the end when they both threads finish? 3, right? Right. But it's not guaranteed to be the case if this is a floating point operation, if this is a float type in Java. Now, because of associativity. Now, the constants here that I picked, this will be the case because it's 0 and 1. These are simple constants. You can find other constants, and I found some other constants. You can pick constants like, you know, let me see how many zeros I even have. I think it was 1, 2, 3, 4, 5, 6, 7, 8. And so if you play with these constants here, for this 1 and 2, you will be able to see that for certain executions, certain interleavings, okay, this, I mean, two different interleavings, you can just simulate one interleaving this way, one interleaving the other way, and you'll see different results. So your job is to find the constant here, the initial value for the variable, and this constant here, and this constant here, and I'm telling you already two constants that you can use, okay, so that you can get different values here at the end. Essentially, one will get 0, one will get 1. Okay, so you'll find some values here for the constants, and then these are some constants you can play with. Make this a float, let C be of type float C, and then see how different executions, so if this is like 1 and this is 2, the execution 1, 2 is going to produce different value than execution 2, 1. Okay. Because of floating point non-associativity. You should do this. Find the values and run it, and you'll see it. So be careful when you're doing, so this happens in HPC computations, where people say, I have an associative operation. Let me just let them, no, you have to be very careful here. And unfortunately, in practice, the error is small. It's a small error, but it accumulates over time. And then trouble can happen. Okay, so just be aware of this. You should have learned this kind of thing in the intro to programming. The non-associativity of floating point is very important. But if you don't know it, that's fine. It's here, and then it can interact with concurrency. Even when you have locks here, even when you have locks, everything is locked correctly, everything is good. You're expecting a deterministic result. Determinism is just difficult to achieve when you have floating point operations. Okay, so just keep that in mind. Okay, so that's it as far as, I think that's all I had for you guys for synchronized. So there is the floating point, there is this weak atomicity business that it's only atomic with respect to itself. There is deadlocks here that we saw in the beginning, and there is this pessimistic versus optimistic, and the fact that, synchronized is kind of a control-centric view of the world. And synchronization does not enforce non-determinism directly. You need to be a bit more. You need to be a bit more careful. Okay. Any questions here? Because we're not going to look at synchronization more. Yes.
Atomic, is it a keyboard? You mentioned atomic.
Yeah.
Is it a keyboard?
So some variants have it. I think the mainstream does not have this atomic keyword. So most people just use synchronized here. There is high-level atomic data types that you can use, like incremental register and whatnot. Yes.
The languages which are like pessimistic by nature, and you have to actively breach something
Yeah.
to access it.
Mm-hmm.
It's not that you synchronize something, but you actively breach it.
Yeah, so there is languages which are not so popular, which are synchronized by default. Everything is somehow atomic or deterministic by default. Later, when we look at when we look later at programming models, it will be such programming models where deadlocks and certain concurrency bugs are impossible by construction of the language. They're usually good in specific domain, more domain-specific scenarios. That makes sense. There, you see it. So yeah, make a note of this. We'll see a language which is by construction, no deadlocks, for instance, which is good. Okay. So this problem, by the way, for your information, because while we are on this slide, this problem with handling floating point soundly, William Kahan got a Turing Award for, which is the Nobel Prize for Computing from Berkeley. And turns out that it is critical to handle it properly if you want to prove anything about deep learning. This problem here. Side point, if you're thinking deeper here, you see that you can start asking yourself, what's the quantification on the bound of the error? So at every statement can start inducing bounds on the error of floating point, and you can quantify this. Separate point, not relevant to here, but it's just again with floating point. It's good to know some of the basic properties of floating point. Okay, that's it as far as synchronization. So there are like few points that we covered, and you are aware of it now. All right. So actually, there's one more, but this will not spend. Why? What? So here, and somebody asked this. Actually, somebody said, "What happens if you get? What happens with synchronized if, for instance, an exception happens?" I have synchronized. I have some function that is long computation. Is doing long computation. Something, updating arrays, adding something, I don't know what. At some point, though, right after it's done, I do division by 0. Boom, exception. Immediately, right? Okay, there's some other code after the division by 0. So what's going to happen to my lock that I took there with the synchronized? Am I going to unlock it? Where exactly? As a programmer, what should I expect here when exception happens? Comments, thoughts. What's supposed to happen here with the lock? I took it, but I'm interrupted in the middle. I mean, what do you want to happen? What do you think should happen? It's a programming model question. I mean, it's Yep.
Further exception, the lock should unlock, and then the exception can convert it.
What you're saying is that when the exception is thrown, the lock is unlocked, and then you can handle the exception, right? That's one view. Yes. Any other? So just be aware that Java is language, right? Has these things, but it imposes a particular programming model on you, right? To synchronize the nestedness and all these kind of things. Yeah. So what happens here is this is by the way a great case to look at bytecodes, a tiny amount of bytecodes, and you can actually look at this amount of code to understand what happens. We're not going to look at it now because this will take us another 10 minutes. But essentially, what is going on here is that if an exception gets thrown where pp is equal to 1, here it can't because pp1, right? But the JVM still treats it as if exception can be thrown. The bytecode still treats it as if exception can be thrown. What it's going to do it's going to have a special section in the bytecode that if an exception is thrown to release the locks. So the locks get released. Okay, so the locks get released. All right, that's important to know. And once they get released, you get access to the exception object, and then you can treat it as normal. If you want to see how they get released, then you can do the Java P and see it. Yes? Yeah, the lock will be unlocked. I will not do it now for you guys, but this is why I told you. You need to... What is going on, my friend? So here, for instance, it looks like this. You cannot see it from there. There's a bunch of instructions here, and there is a bunch of tables here in the bytecode that tells you what to do with the exception and where to release the lock, so you can see it over here. Okay, and over here, once the exception is thrown, there is something called monitor exit. This is the unlock in the bytecode. The best way for you guys is you just take the instructions from the website and just run Java P, and you'll see this code, and you can understand it. If you have questions, ask. But as far as programming model goes, the locks get unlocked here. Like the lock is going to be released. So it's not like exception will happen. Let's go back to the previous slide. And suddenly you're going to exit the method foo with the lock holding the locks, because then this will be all kinds of trouble. You're holding locks and going down the stack trace somewhere else. Exception happens, locks get unlocked, then you get out of the method here, and you continue down. Whoever called foo, but with the locks unlocked. Okay. Does this make sense? Yep.
If the exception gets catched,
yes.
inside the synchronized block, is the lock also
So the question is, if the exception gets catched, if the exception is caught inside if you have like something like a try here, right? Yes. So when you exit the block, the synchronized, then it will get unlocked. So let's look at it here in more detail. Over here, let me show it to you. So the lock will not get unlocked immediately. It will be in your exception. You have the lock when the exception gets thrown, and then when you exit the exception handler, then it will get unlocked right after this, after your exception handler. Okay. So there are many such weird corner cases, by the way. I mean, this is not a weird corner case, but how it interacts here with exceptions, how it interacts with sleep, how it interacts with other things that you guys have to, I mean, the best way is just to run it and see what happens. There's just too many of these corner cases that can happen that you have to play with here. So what else? So that's as far as the synchronized and exceptions. The last point about synchronized before we go to wait notify is what happens is that we didn't talk about this, but synchronized, if you remember the previous lecture in this room, we talked about the native layer. The only thing you need to know for now is that there are special instructions in the hardware, special provided atomic instructions called compare and swap on certain architecture, or load, link, store, conditional. We'll look at these instructions, which are used to implement the lock. The synchronized lock. The JVM uses them. Okay. So this is how it is as far as let's make a note of this. We'll not look at the instructions now. They're just some low-level instructions that we'll get to it. We'll get to it later. Okay. Now, any questions so far here? Yes.
Is there any way to exit a synchronized blockchain truly? So is there a kind of statement, like a break statement or a while loop?
I mean, you can exit it with a return if you want, and you will release the lock if you do this. Yeah, just a break. It's just a return, yes. So the return, if you do return inside synchronized, is going to unlock the lock again there. It really wants to make sure that if you have a synchronized block, no matter what happens there, exceptions or whatnot, when you exit the synchronized, the locks are released. Just to make sure that the color of the method is kind of clear what has happened, okay? All right, so what we'll do, if you have additional questions on synchronized, so we only spend time on synchronized here. okay? Because it's so important just to have a feeling for synchronized, okay? So we have, next time we'll wrap up this wait notify, and yeah, I'll see you, I guess, Tuesday. So.